Welcome to today's webinar, which will focus on CAN bus telematics and how you can set this up with our CANedge CAN and CANedge free devices. And I'll also be covering a number of topics related to data lakes. A lot of the stuff I'll be covering here is also detailed in an article that you can find in the description. So if you feel that some of the topics are glanced over a bit quickly, feel free to check out the article for a more detailed walkthrough. The topics I'll cover will be a brief introduction and then just briefly recapping the basics of the CANedge. But a lot of this is also covered in a previous webinar we did about a year ago called CAN bus data logging. And you can find that on our YouTube channel, and it goes through some of the basics of the CANedge and the software in more detail than I'll do today in this webinar. After this, I will cover a bit about device fleet management. So how do you handle when you have a number of CANedge CAN devices connected in the field? Once we've covered that, I'll go through setting up a number of backend processing infrastructures and what you can use these for in order to get the most value out of the CANedge that you deploy. Then we'll switch sides and we'll go to the front-end side and look at how can you visualize this data that you have now prepared in the backend, and how can you also set up more advanced analysis of the data. And finally, I'll cover a few use case examples and we'll do a bit of Q&A where you can essentially ask questions in the chat. So if you have any questions throughout the presentation, feel free to write them in the chat and I will try to cover them at the end. So I'll aim at about an hour, maybe an hour and 15 minutes for the webinar throughout. Briefly about CSS Electronics, we were started in 2015 and we're based in Denmark. And our specialty is CAN bus hardware, in particular CAN bus data loggers is our focus, but we also have a number of sensor to CAN modules. We also have quite a lot of popular CAN bus content, so you may have seen us from different introductions on the CAN bus related protocols, and you can find all of those on our website under our guide section. Today, our products are used by more than 5,000 companies across the world. You can see some examples below. And probably 80+% of our end users are OEM engineers, so equipment manufacturers and the engineering teams working there. And in particular, this is heavily in automotive, but also industrial and maritime industries. My name is Martin Falch. I'm one of the two co-owners at CSS Electronics. My background is in quantitative economics and time series econometrics, and my main responsibilities at CSS is on the sales and marketing side, but also technical sparring and support with all of the engineers we work with, as well as development. So a lot of the stuff we'll go through today in terms of the cloud infrastructure is stuff that I've written, and you can always reach me if you have questions on setting this up on your own. The CANedge is our primary product, our CAN bus data logger series. And we have a couple of variants of these that I'll just cover briefly. The CANedge 1 lets you record CAN bus data to an SD card offline. The CANedge 2 does the same, but also allows you to offload this data via Wi-Fi to your own server. And the CANedge 3 is like the CANedge 2, but instead of Wi-Fi, it supports LTE, so 3G or 4G. And as you can see from the overview here, these optionally come with GPS inside so that you can get position and speed and trip distance and acceleration rates and other information along with your CAN bus data. If we look at the CANedge 1 at the very core of it, this is a device that is designed to be highly plug and play. You can connect it to your CAN bus and it will immediately start recording any CAN bus data that is there by detecting the bit rate and recording that data to the SD card. Then you can disconnect it and take out the data and start analyzing. But at the same time, as mentioned, we sell to engineers and therefore the specs of the device are designed to cater to the requirements of these engineers, which means that you can record thousands of frames per second without frame loss. The device has 2 CAN channels with support for CANFD, 2 LIN channels, it supports error frames, and it timestamps your data at a 50 microsecond resolution. So in other words, this is a quite specialized tool designed for these high intensity and high performance use cases you might encounter. At the same time, we try to make it extremely compact, as per the picture here, because these are deployed in anything from big automotives to small e-bikes, and being able to deploy it easily is quite critical. By default, you will record all of the data that you record with the CANedge, but you can configure this a lot, as we'll get into in a bit, and you can also do a lot of other advanced stuff with the configuration to customize the device for your particular use case. At the same time, security is a big factor for our devices, as we'll also cover a bit later, and interoperability is also critical. We don't want to lock anybody into using a specific piece of software. We try to make it possible for you to use whatever it is that you prefer to use for analyzing your data. As mentioned, the CANedge 2 is essentially a CANedge 1 but with Wi-Fi, and that means that you can offload the data to your own server via a Wi-Fi router. And the CANedge 3 is the same, but here you insert your own SIM card, and now the device has internet connectivity and allows you to offload data to your own server again. And the way that works is illustrated here. When you have a CANedge 2 or 3, you'll want to set up your own server, whether it is Amazon or Google Cloud or a self-hosted server. So you deploy that in advance, and importantly, we do not host it for you. You have to set this up yourself, but we make it extremely easy to do. So setting up an Amazon cloud server should only take a few minutes once you've created the account. So we try to make it extremely quick to get this up and running, and you have the benefit that we are not involved in your data, there are no other parties involved, and you pay much lower rates because there is no man in the middle here. Once you've set that up, you want to provide the Wi-Fi details or the SIM card details to the device as well as part of the configuration. And you do this through a simple configuration editor where you then put the updated file onto the SD card of the device, and now you're done. The result of this is that once the device is now deployed in your vehicle or machinery, it will automatically record data to the SD card, and if there is connectivity, either through internet or through a Wi-Fi router, the data is automatically offloaded from the SD card to your server, and once successfully uploaded, it will be deleted from the SD card to make space for new data. And this also means that if there is a period where you do not have coverage for whatever reason, then the data is not lost, it is always just accumulating on the SD card and being offloaded, and all of this happens automatically. So that's the super quick version about how the CANedge 2 and 3 actually work. But managing this, if you get more than 1 or 2 devices, does involve some considerations. And I'll try to cover 7 tips and tricks here in this section about how you manage the devices in your fleet as efficiently as possible. The first step is to make sure that you select the right server for storing your data as well as processing your data. And as I illustrated before, there are quite a few options because at the end of the day, the CANedge allows you to connect and upload data to any S3 compatible storage. And in layman's terms, that's just a way of storing files in a server in a modern way. Some of you may be familiar with FTP, and S3 is a bit like a modern equivalent to that. So you need a server where you can store files in a structured manner using this S3 interface. And all of the ones illustrated here will support that, but I personally recommend that you use Amazon Web Services for a couple of reasons. First of all, this is the most used cloud solution globally, and it's also where the S3 storage interface originates. So it is fully native to AVS, which has a couple of practical advantages for larger scale deployments. We also make it super easy to integrate with AVS because it is the most used server for our end users, and we therefore provide some automation tools. That means that you can set up whatever infrastructure you need in a few clicks. You can also set it up for the other solutions, but it is a bit more of a manual process there. By using a cloud server like AVS or Azure and Google, you also have a 100% scalable setup. So you can start with one device, but you can use the same solution for 500 devices or more. You don't have to worry about, purchasing more storage or whatever it might be. All of this is elastic and happens under the hood, and you just connect more devices without necessarily having any concern about, whether the server is capable of handling it. This is different if you self-host your server with, for example, MinIO. then you need to consider both the computational resources of whatever is hosting that server, and of course whether you have sufficient storage for handling, the amount of data that is coming in from our devices, which can be significant. Importantly, AVS also only costs $2 to $3 per 100 gigabytes per month, or $0.023 per gigabyte. And I think this is a bit overlooked sometimes, that I don't like Jeff Bezos more than the next guy, but it is extremely cheap to store data in AVS. And for this reason, I don't think it really makes sense to consider necessarily, for example, self-hosted solutions if you're going to scale to large volumes, because the cost of managing a self-hosted solution doesn't really make up the cost you might save in storage in this case here, at least in my opinion. And finally, it will be a lot easier to deploy many of the infrastructure items that we'll discuss through this webinar here. When you've decided on the server, another step that you should consider is how you set up what is called a bucket. And for a simple setup, you might just have one bucket, which is like a folder in the server where you point your devices to and they upload files inside this folder, and that is how you structure the data. And for simple setups, you'll just want a single bucket, and the only thing you have to consider here is to make sure that the bucket is located in a region that is close to where you are deploying your devices. And this is important for the speed of data transfer. It is also important for when you are actually going to analyze the data later on, because this reduces the latency when you are working with the data from the S3 bucket. So in other words, if you are deploying in Germany, make sure to select a region that is, for example, Frankfurt. Do not use US East 1 as an example. This also means that if you are going to deploy devices globally across different regions, you may need to have more than one bucket. For example, as illustrated in the visual here, you could have a bucket for North America and a bucket for Europe. Don't go into creating, a bucket for every country in Europe you might be deploying. The impact is not significant enough for that complexity to be warranted, but it does make sense to have maybe one or two regional buckets. Another consideration is if you are going to use the CANedge to collect data from different clients where you wish the clients to have access to this data. Like maybe you are an integrator or an analytics service provider that wants to, visualize data on behalf of different clients, or you are an OEM that sells, heavy equipment to 5 different customers and you want to provide data logging and telematics on top of this. Then you may want to create a separate bucket for each of your clients in order to keep all of their data and all interaction with that data 100% isolated from each other. So that's another good reason for creating multiple buckets. So as illustrated here, just make sure this doesn't go out of hand. We recommend to stay, within a reasonable number of buckets to avoid having to manage, 100 different ones. Another thing you need to consider when you deploy a fleet of CANedge devices is whether to go for Wi-Fi or cellular. Wi-Fi is great if you control the Wi-Fi. So if you're going to connect the device to stationary assets, for example, in a lab where you have full control over the Wi-Fi, then the CANedge is definitely the way to go because you essentially save on LTE data transfer costs and it's quite simple to work with. But if you are, for example, again deploying on behalf of a client and you don't have direct control over whatever Wi-Fi is available, then this can quickly get very complex if, for example, the controller of the Wi-Fi network decides to change the name, change the password. You would need to know this in advance to manage the devices and update them before these changes take effect, otherwise they will go offline. So in such a scenario, the CANedge 2 with Wi-Fi is not necessarily ideal. The CANedge 3 offers a direct upload via 3G or 4G, so you insert your own SIM card. And obviously, this is nice if there is no Wi-Fi available, like if you have mobile equipment that is operating on the road and you need to collect this data all the time, and you can't rely on these vehicles, for example, returning to a specific Wi-Fi area. Cellular is great for that. But similarly, if you are simply not able to control whatever Wi-Fi might be available, this is a more scalable way of ensuring that you always know that the devices can connect to the internet because you own essentially the SIM card and you have control over that aspect of the connectivity. So Different scenarios may warrant different devices, and you can easily mix these in a fleet as well. Once you've decided on your device and set up your server, it's a good idea to just get started and record some data. But as you progress, you will want to consider some configuration of your devices in order to optimize the configuration. The most obvious one that I recommend is to almost always enable compression of the data, because you reduce the size by 50% and there is not really any cost to it other than the data needing to be decompressed once you need to process it. And for all of the infrastructure that we'll cover today in the cloud, this is done automatically without any distinction as to whether your data is compressed or not when it is uploaded. But as you can imagine, for example, the CANedge 3, it is quite critical to reduce the LTE transfer cost by 50% without any downside. So definitely consider this, and it's easily enabled in the configuration of the device. Once you go a bit further, another critical thing to consider is if you can filter some of your data. Let's say you have a truck and you are recording 80 unique CAN IDs from this vehicle. Maybe you need all of that data, and maybe you need it at the raw frequency. If so, that's great, just record everything. Make sure to compress it. But for most use cases, even for diagnostics or whatever it might be, there are probably 20 to 30 and sometimes much more % of these CAN IDs that you don't actually need for your particular analysis. So you can filter these out using the configuration filtering. And for the CAN IDs that you do need to record, you may not need them at the raw frequency. So for example, RPM may be broadcast on the CAN bus 100 times per second. But for your analysis, you may be okay just getting it 10 times per second. And you can imagine that if you start using filters and prescalers like this, you can typically achieve a 90 to 95% reduction in your file size while still getting what you need for your analysis. So this is critical, and it's particularly critical as you scale up your deployment. You also want to consider a few other things. Triggers let you start and stop the logging as well as the transmission of data based on a CAN signal, like start logging when engine speed is above 500, stop logging when it goes below 300, whatever it might be. You can set that up quite easily in the configuration, and it can also help you reduce the amount of data you record, as well as ensure that you do not transmit data when a vehicle ignition is off while the device is still powered on, for example. You also want to consider what the split time or size is set to in your configuration file. So you can control how frequently the device generates a new file, and maybe you want to generate one when it hits 5 megabytes or whenever 30 minutes have passed. That is up to you. But this is something you control in the configuration, and indirectly, this will affect how frequently data arrives at your server. So in other words, this is also the way you control the upload frequency to your server. You can in principle set this to 10-second splits to get near real-time data transfer, but creating smaller files has downsides when it comes to the efficiency of your post-processing, and it also adds some overhead, meaning that the costs of transferring, let's say, 1 gigabyte of data will increase slightly. Other things you can consider is if you have a GPS inside the device, consider using centrifusion so that if you are in an automotive deployment, you improve the accuracy and ensure the device can retain GPS fix even when it moves into a tunnel or like a parking lot for a period of time. And you can also use the GPS to synchronize the real-time clock of the device. What this means is that every device in your fleet will stay within a plus minus 200 millisecond precision of the GPS-based absolute date and time. That's nice because then you know when an event happened in one device and maybe another event in another device, you actually can compare the timing in absolute time or in absolute sense. And finally, for those advanced users that absolutely need to ensure that you do not lose a single CAN frame, it can sometimes be relevant to consider whether your bit timing and bitrate settings are fully matching your CAN bus. This can be checked by enabling error frame logging in the device and looking for whether there are some periodic errors, maybe 0.1% or something like this. If there are, then you can look into potentially testing out an alternative bitrate configuration that may allow you to record the data without any frame loss at all. In addition to this, you will want to consider security measures when you deploy the devices. The most important one, in my opinion, is that if you are adding a Wi-Fi password and a server password, for example, to the device, these will by default be in plain text, meaning that anybody with access to the SD card can simply extract the configuration file and access your server. And obviously, you don't want that. So you encrypt that as per the documentation in the CANedge intro in order to ensure that nobody can read these sensitive information. You can also enable what we call log file encryption, where you ensure that the data is stored in an encrypted manner, so nobody is able to read the data and nobody is able to manipulate or inject information into the data. This is critical if you're doing, warranty dispute handling and you want to prove legally that something happened, where it must not be the case that you could have manipulated this event in the data. But it's also critical if you're recording data in Europe or California, where things like GDPR may mean that you must not record GPS information and other stuff that can be linked to a specific person. In addition to this, you should consider data transfer encryption, so TLS, to make sure that the data that is uploaded from the device to your server, that transfer is encrypted. You also may want to consider using more strict device policies for the connection of the device to your server. We choose some pretty strict ones, but you can go a bit further if you like. And similarly, for anybody with access to your server, you should make sure to manage the user access in a way that ensures that they have minimal access rights. So don't give everybody the possibility to look into whatever or to modify whatever they want in your server. For example, doing over-the-air updates and other things. So limit this by providing, for example, read-only access to certain users. If you go really big, like some of our customers do, and deploy thousands of devices, then you need to consider some things about commissioning these efficiently. So you don't necessarily want to take every device from us off the shelf, add your own configuration manually if you can avoid it. And you can do so by asking us to deploy the devices or sell the devices to you with pre-configured custom configuration and also your own TLS certificates if needed. And what this means is that you can then directly deploy the devices, or you can set up more advanced workflows as illustrated here, where you might ask us to put in the details for an S3 deployment server or bucket where devices then initially connect to, and then you have some automation routine that maybe once per hour checks if a new device got connected, and then it automatically updates this device over the air to shift it over the air to the production bucket. That is the one that is perhaps containing more of your sensitive information. So different users may prefer to have these workflows to stay really strict on security. And as another note on this, it can be a good idea when you deploy many devices to note down some meta information about the devices, like illustrated here. And a lot of this you can get from storing the device.json file, which is a small file that you find on the SD card of the device, and which is also uploaded by the device to your S3 bucket. Finally, when you have your devices connected to your server, you will need to keep track of them. Because while this all runs autonomously, if something happens in the field that might cause issues, you need a way to quickly identify that maybe a device is no longer uploading data as expected. Maybe a device didn't get updated with the latest firmware for whatever reason, or maybe a device is having some other issues. And CAN Cloud is a free browser-based tool where you can log into your own server and monitor your devices in an easy manner using the dashboard you see here. But we also have some users that set up more custom solutions using the open source S3 API, where they set up automation to look for certain events on the connected devices in order to manage this at a larger scale and set up notifications and alerts based on this. So this was all about the initial step of your workflow, essentially collecting data from whatever it might be, machinery or vehicles or maritime vessels, to your own server. So essentially the part you see here. When the CANedge is connected like this, it will be recording raw CAN bus and LIN bus data, uploading this in log files, essentially called MDF log files, a specific file format, to that server. And this data is not necessarily human readable by default. It contains CAN IDs and data payloads, and you will need to decode this data in order to make it useful for further analysis in most cases. And as the other webinar we have on CAN bus data logging explains, this is typically done using something called DBC files. So for a specific vehicle, you will need to have the DBC file for that vehicle. Then that file together with the raw data will allow you to decode the data into human readable form, where you can visualize things like temperatures, state of charge, alerts, whatever it might be. We provide the software tools that you will need in order to decode the data in this way, as illustrated here, but you will need to have the DBC file yourself in order to fulfill this here. When we talk about data pre-processing, it is essentially the process here of taking that raw data, taking the DBC files, performing some form of processing of that data, essentially as a minimum to decode it with the DBC file, and then outputting a new file format or new form of the data where it is more close to what you would want to analyze in the end. And I'll explain in more detail what we mean by that. But this is essentially the processes of pre-processing the data. And you might ask, why would you want to do this pre-processing? Why not just process the data whenever you want to work with it? And for some use cases, this is fine. I mean, if you have a single log file and you're doing some ad hoc analysis on your laptop, pull that file to your desk, open it in one of the GUI tools, DBC decode it and visualize it, and that's pretty straightforward. But if you have 10 gigabytes of data, for example, and you're trying to do some analysis based on this, it might take hours to decode it and make it readily available. So you will want to shift that time consumption to not be the time when you want to do your analysis, because you would be wasting time looking at your screen, which is quite annoying. So it allows you to separate that timing of the pre-processing versus when you actually analyze the data. But in addition to this, the pre-processing also allows you to put the data into a format that is more compatible with other tools. So there are some tools that allow you to take the raw data from the CANedge and work with that, but a lot of tools that you may be interested in using will be much more easily accessible, or the data will be more easily accessible to those tools in a different format, which I'll explain in a moment as well. In addition, you don't want to do the process of decoding and processing your data multiple times. So again, if you're doing some analysis on 1 gigabyte of data, you can pull it, you can process it and analyze it. And then a week from now, you may want to do some additional analysis of this, but then it's annoying if you have to do that pre-processing again. So you avoid this here. And in particular, if you're gonna do big scale analysis that might go beyond the memory of what your computer is able to handle, then it's also nice to have it in a format that is well suited for that. We have an infrastructure that we recommend for solving this, and here I'm showcasing it for the case of Amazon, but as you'll find in our guide, we have equivalent workflows for Google Cloud and also for Azure. So it's not limited to Amazon, but this is just what we use in this illustration here. Essentially, the first part of the workflow is what we already discussed. A CANedge is uploading data to your cloud. This data ends up in a input bucket over here, where the MDF files with raw data are stored. But then some additional stuff over here is added, something called a lambda function. We also have an additional S3 output bucket, and then we have something called Athena over here in this workflow. And I'll get into these in a moment in detail. Something that is important for me to mention is some of you may get scared a bit by some of these infrastructure resources that I'm mentioning. And I understand that, because not all of us are cloud engineers, and probably less than 1% of our end users are familiar with Amazon before they start working with the CANedge. So in order for us to enable our end users to still deploy some of these workflows that are quite advanced, we essentially create a small recipe, as you might call it, a small file that details what should be deployed in what way within your account. And all you then do is to load this file and say, fill out a few blanks and click deploy, and then everything is automatically deployed in your cloud server. And that means that a process that might take hours normally to set up, if you were to do it step by step, can be set up in a few minutes by using this process here. If we look at the first step in this workflow here, something called a lambda function will be used to process the data. And the way this works is that when one of your CANedge devices uploads a log file to your S3 bucket, an event will happen. And the S3 bucket essentially determines that now a new file was uploaded, and it will trigger this lambda function and tell it to process that incoming data. And the lambda function is essentially just a way of running a small Python script on that file that was just uploaded. And what happens in this Python script is essentially that it takes the file that was uploaded. It also takes your DBC files, which you have put into the input bucket, where you also have your raw data. It essentially downloads these two components into a local Python environment, and here it runs it through something called an MF4 decoder. This is a piece of software that we provide free of charge, that it will allow you to take the raw data, take the DBC file, use those two components to decode the data into, again, temperature, state of charge, and stuff like that. And it stores this decoded information in something called a Parquet file, or multiple Parquet files. Parquet files are a bit like CSV files. You can open them and show them just like a CSV file, and you would see timestamps and columns with a column for each of your signals. So very similar, just better. So faster, more efficient, more compact than CSV files. And they are a smart way of storing decoded data in a compact manner. This data is essentially written by the lambda function, or uploaded by the lambda function, to another folder in your server, another S3 bucket. And we call this the S3 output bucket. And this is where we store the Parquet files, as I explained in a moment. But the lambda functions are pretty cool. They are very low cost, as illustrated here. And they are easy to deploy because this is basically handled by this automatic deployment that we just described. They trigger automatically whenever a log file is uploaded, and the processing is immediate rather than some periodic processing that happens every 1 hour. So as soon as data is coming in from your CANedge, it will be processed within a matter of seconds and therefore be available for consumption in whatever frontend you will use to analyze this data. The lambda function is also serverless, which means that you do not pay for this at all unless something is being processed. So you pay when it is active and processing data, but when you don't have any data uploaded by a CANedge, you don't pay anything for this. As mentioned, these Parquet files that are being created, they will be put into another S3 bucket. So a bit like how the CANedge stores your raw data in what we called the S3 input bucket, we are now going to store this decoded data in the other bucket called the S3 output bucket. And we store it in a way as illustrated here, with a folder for every device ID, so for every unique device in your fleet. And then you will have a folder for every CAN message. And within this, you will have the year, month, day, and then the actual files stored in here. So this structure is highly efficient and has some benefits that are sort of a bit technical, but means that you can access the data in a very efficient manner. But what is really cool about Parquet data lakes is that they are extremely low cost. Just like AVS and storing your raw data is low cost, storing your decoded data in this way gives you a bit of the experience like if you were storing it in a database. So it's very fast to query and very fast to extract information from, but you pay a fraction of the cost that you would in comparison pay by storing this in a classic database in the cloud. So for this reason, we think it is very well suited for these use cases where you have hundreds of gigabytes of data and sometimes terabytes of data. At the same time, Parquet is extremely popular. It is the most popular file format for this type of use case here. And that means a lot of tools will very easily be able to work with this Parquet data, as we'll see a bit later. Finally, you will want to set up something, or the automation workflow will set up something called Athena. And Athena is essentially a way to access this data in your data lake, but super fast. So what Athena does is essentially that it provides you with an interface where you can write something called SQL queries. And that allows you to say, okay, give me average speed for a specific set of devices for a specific time period. And then Athena will crunch, potentially gigabytes of data from your data lake, and it will return you, 2 kilobytes of data containing just the actual response or the actual result of this data. And that means that it's well suited for different things like dashboard visualization, as we'll see later, but also a lot of analysis that may involve this type of extraction of results and aggregations. Again, Athena is interoperable and supported by a lot of tools, and as illustrated over here, it uses SQL queries or standard SQL, and I understand if you haven't used SQL before, this may not make a lot of sense to you, and that's perfectly fine. You don't need to use or to understand SQL necessarily in order to use this, because for the deployments where this is relevant, we will provide you with, you can say, plug and play query examples to let you do what you need to do, and you will only need to replace things like, the table name and the message name or whatever it might be, a signal name here. And then you can essentially extract data in a very efficient manner from your data lake. And I'll explain more about how this works in different contexts later. If you want to do some advanced stuff in SQL, you are also able to do so. And personally, my experience is that something like ChatGPT and similar chatbot solutions will allow you to very quickly generate quite powerful SQL statements that you can then test out very quickly for different use cases. Once you have this basic workflow up and running, where you are processing data automatically as it's coming in, and you're writing the decoded data to a data lake, you have the benefit of extending this very easily with additional functionality that might be relevant for your use case. One example is what we refer to as event detection, essentially spotting when something of particular interest to your use case happens within your data, and then doing something based on that event. And you might ask, why is this relevant? Well, setting up event detection as part of this workflow we discussed here has a number of benefits. First of all, if you deploy event detection in the way we will illustrate here in a moment, you will automatically be evaluating 100% of your data. And as we described just before, the Lambda function we already set up is doing this, right? It is processing every log file that is coming in. And what that means is that if you need to do something that essentially involves scraping through every single log file that is being uploaded, for example, to determine if something critical has happened, like a temperature threshold being crossed, then this is a nice way of doing it because you are reusing that existing 100% processing of your data. And as you can imagine, having that analysis or that event detection set up in an automated manner can, to an extreme degree, supercharge your diagnostic ability. If you are looking for, diagnostic trouble codes happening across a fleet of 50 tractors, for example, you can go through thousands upon thousands of log files manually or looking at the data. You can write complex Python scripts to do it. But with this approach here, all of this will be done automatically, and you can just, browse through the events instead of looking at, all of the log files. The workflow will also allow you to get immediate notification when one of these events occurs, either by SMS or email. And again, this is super powerful because if you have something critical that you want to be notified about, you can get immediate information about this. An example being some of our users that deploy this for predictive maintenance, where they wish to be notified as soon as possible if, for example, there is going to be a thermal rundown event in one of their automated guided vehicles. The way that you can set this up reuses the existing infrastructure that I just mentioned before. So you again get one of these recipes from us in the guide that will deploy some extra stuff in your cloud that will allow this workflow to work. So this is basically me saying, don't worry about it too much. A lot of this is just going to be deployed. And the main thing you have to worry about is what we describe here. Because we, of course, cannot know at CSS what type of events you are interested in. This is completely up to the specific use case. So instead, we make it quite simple for you to define these event objects where you essentially describe what are you looking for. An example is illustrated here, where you might be looking for high-speed events. And in order to detect this, you need to inform a couple of different things, like what you want to call the event. Here we call it high-speed alert. What message is the relevant signal stored in? Okay, in this case, it's stored in the internal GPS of the CANedge 3, for example, in the message called GNSS speed. And the trigger signal we're interested in is simply called speed in this case here. Then we want to define a lower threshold and an upper threshold. And this is a bit technical, but you typically want to have these multiple thresholds in order to not have, an extreme detection of events when the data is flickering around a certain value. And in this case, we define 20 meters per second and 22 meters per second as the thresholds. And we tell the event here that we are looking for events where the data is, or where the speed value is crossing from below 20 meters per second to above 22 meters per second. And as illustrated over here in the plot, you will see the value of speed as the blue line. And you can see an event happens here where the data crosses the red threshold after having previously been below the green threshold. And this happens a couple of times here in succession, and again over here. And all of these will be considered separate events because this log file could have been, multiple hours, for example. We want to capture each of these events as isolated ones. But we also want to ensure that when the Lambda function is processing this particular log file, it doesn't send, 5 or 4 alerts by email. So only a notification is only sent on the first event here in a specific log file processing. The data around this event is stored again in a Parquet file, and you can probably spot a theme here. You already have a Parquet data lake set up for your other data, so let's reuse that. Store this event information, which is a bit like meta information, in essentially small Parquet files, and we also put those into the Parquet data lake in a separate folder. And the contents of the file can be shown in something called TAD, which is a Parquet viewer. And you can see, we store some timestamps around the event, the name, the device ID, the event ID, the signal name that was relevant, and some other information, potentially also the position of the event if we have GPS data available. So this is essentially put into the output bucket here. In addition to this, we also trigger something called an SNS topic. And again, this is something that Amazon provides as a method for sending emails or text alerts to subscribers. And by default, you will typically just add your own email as the subscriber for this, but you can add more if you want, and you can also not receive these notifications if you want. Here is an example where I'm getting an email because my own car entered Copenhagen at a specific point in time, and I see the device ID and I get some basic information, and this is of course something you can customize as you see fit. Event detection is one thing that is really useful when you are looking to spot specific intermittent events, and you might only, capture a couple of events over a 1-year period of interest per device. Another way to look at the data that you might want to consider is to aggregate it to a specific level. And because a lot of our users are within the automotive industry, what this aggregation is typically surrounded by, or the way you aggregate the data, is typically in the form of trip summaries. So you have a car, for example, or a truck or an e-bike, and you want to be able to understand what is the behavior of this vehicle at a trip level. Like what is the max speed per trip? What is the average speed per trip? What is the average state of charge consumption per vehicle trip, for example? This kind of stuff requires that you find a way to aggregate your data to a trip level, which is not easy to do. And you may also want to add some additional meta information to enrich that data and make it easy to work with for your analysis. And the reasons we think this is important is that the existing setup we have discussed so far allows you to very easily look at a single device and look at a specific period of time. And you can analyze the device very efficiently in this way, but without any real knowledge or consideration of whether that time period constitutes a trip or multiple trips or no trips at all. But if you want to look at things or your data across multiple devices and also look at it across trips as a dimension, you need a way to enable this automatically, because otherwise you'll be writing a lot of code just to facilitate this. And that's basically what our trip aggregation methodology automates for you. So again, this is an infrastructure item that you can set up to enhance the data that you're already decoding and processing. Essentially, this workflow will automate the trip separation, and it will allow you to scan much less data when you're doing these high-level analysis across, let's say, 50 devices, 3 years. You can easily imagine that if you're just looking at the average something per trip, rather than scanning through billions of data points, then it's of course much cheaper and much faster to do. And it also allows you to browse your data much more easily and speed up your analysis. The way we recommend to do this is essentially to deploy a periodic Python script that on a daily basis goes through the data in your data lake and aggregates it. And the way this works in a bit more detail is that you essentially need to specify what data do you wish to aggregate in what way. And we provide a JSON structure, which is a small text file structure where you can specify this. And in the example you see here, we have defined a cluster 1, which consists of 3 devices. And for this cluster here, we want to identify trips based on the GPS speed. So essentially, we say, whenever we have a period where there is no more data for the GPS speed for 2 minutes, for example, we consider that, to be a trip distinction or trip identifier. And we then, using that information, we can then identify windows of trips and separate them in that manner, and then perform all subsequent aggregations based on those trip windows. And down here we say, for example, that we would like to get speed as one of our signals that we aggregate. We want to get the average value and the max value. But you can also do more advanced stuff. Down here we're saying we would like to get the state of charge, but we would like to take the delta sum of the negative values. So you could imagine a situation where you have state of charge moving over time, and you want to get the consumed state of charge per trip. Maybe that's 5%, 10%, whatever that is consumed. And you need an aggregation method to do that. And this is something that is provided in here as well as one of the default functionalities. This JSON file is put into your output bucket, and then this small Python script that runs on a daily basis in something called glue will pull this file, pull the Parquet data from your data lake on a daily basis, and it will process and extract this information that is specified in the JSON file and put the summarized values into the data lake. And it will do so in the form of, again, Parquet files. And just like the event case, we have, a Parquet file here with, some information, device ID, message, signal name, what is the aggregation type, what is the value, like what is the average speed for this particular trip. Okay, it was 8.51 meters per second. What was the duration of the trip, and when did it start, when did it end? And then we can define a unique identifier for this trip. And as you can imagine, because we have the existing workflow, we can now use this Athena tool to query this data via SQL, just like the other data examples we had before. And that allows you to do things like, extract across 50 devices all of the trips that satisfy certain conditions that you can set up here. You can also add additional meta information to these trips here in order to enhance the data. For example, if you have the identifier of the vehicle and you want to add that in to your data, you can request it over the CAN bus, and then you can essentially pull that out and add it as one of the aggregated measures in your data. This was all on the backend side. And now, as you can imagine, you can potentially set up quite an advanced backend where you both have the basic data pre-processing we discussed, but also potentially event detection and trip summary aggregation. Typically, you will want to then work with this data in different ways. And one of the key ways you may want to work with it is through data visualization. And there are different reasons for why data visualization is relevant. Obviously, it's a common way to extract insights from your data, to be able to do a quick plot, review how it looks, and look for specific patterns in the data, for example. But it's also very useful if you need to report specific results or share data with other teams or with clients or whatever it might be. So having an easy way to facilitate this is critical. It is also, in our opinion, one of the best ways to do this type of ad hoc diagnostics analysis where you're looking at the data and potentially looking at multiple signals at a time in order to detect if a certain event has arisen that might not be possible to detect in a programmatic manner, as we discussed before. And finally, if you're doing some very advanced statistical analysis and modeling, even then, in our opinion, visualization is critical in order to sanity check that your data is as you expect before you just put it into a big advanced model where it can be harder to determine if something was wrong with the input data in the first place. If we look at the solution example we recommend for this, you can see that a lot of this is just reuse. So we already have the entire workflow with the Parquet data lake and Athena over here, and it just so happens that a tool called Grafana, which is an open source dashboard visualization tool, has a data source for Amazon Athena. And we can link these together without doing much more effort than what we already set up in the first place. And the way this works is that when you have deployed the previous backend pre-processing workflow, you will get the login information or the authentication details required for Grafana to connect to your Athena backend. And this in turn allows you to write these SQL queries in order to extract data from your data lake and then visualize this in these Grafana dashboards. And don't worry if you do not understand SQL queries here, because again, we provide a number of dashboard templates that you can get started with, and you only have to modify minimal stuff in this here to customize it for your use case. To illustrate this, check out this sort of dynamic device dashboard, which shows data from a single device, which you can toggle up in the drop-down up here. So if you have 10 devices, you can select between them as you see fit. And you can also add like meta information if you have, this being truck number 1. This can be placed next to this here. You can select the message you're interested in, like the CAN message name and the signals within that message, and you can select aggregation stuff. So in other words, this gives you full access to all of the data in your data lake, and you can decide what you want to visualize through these drop-downs in a dynamic manner in the front end. And you can share this dashboard link to another team, and they can look through the data in a very easy way without having to download anything to their laptops, for example. And if you go to our website and look at the software tab, then we have a link to dashboard playgrounds, and we have a ton of these. You can toggle between them in the upper right corner. There's like a menu here saying dashboards. And you can see here that we then combine the dynamic dashboard functionality we just saw before with more static panels where you can set up whatever is sensible for your use case in order to visualize what you need. And you can find different examples for how this can be used in practice if you go to that playgrounds link and try this out in action. We also discussed the event summary and the event detection before. And since all of this event data, if you have added this event information will also be stored in your data lake, and that means that you can query it just like your other Parquet files. And we provide, of course, a template for doing so easily, which means that you can now look at all of your historical events across your devices or select specific devices of interest, and you can see when they occurred, and if you have GPS data, you can see where they occurred. So you can imagine, for example, that if you are trying to track diagnostic trouble codes in heavy-duty vehicles, you will be able to see for a specific time period where were all the events where a DTC got activated. And you can down here in the table see, which event was it, which device ID was it. And then as something really cool, you can have a small link over here next to the event. And if you click that, it will open up the detailed dashboard for that particular event. So in this case here, I'm visualizing data from my own electric car, a Kia EV6. And if I were to click a link like this, it would open up the dashboard you see here, where I have access to the full resolution data. So not the aggregated one or the event data, but the full resolution data that is also in my data lake. And I can go in and I can analyze it here. And the cool thing is that the link will open up this dashboard with the time period set so that it is centered around the event timing, and then giving me plus minus X minutes before and after this event here in order to quickly look at what was happening when this event occurred, just before and just after. In a similar way, the trip summary aggregation can also be visualized, and here is an example playground dashboard we have for this, again from my car. And this here shows you, a summarization of all of the 1150 trips that I have taken in my car. And you can see things like, what were the top 10 energy consumption trips. You can see these listed over time. You can see the positions of the different trip start events and other information like this. So again, a useful way to get a quick overview of large amounts of data from your data lake. And this brings us to another front-end topic, advanced analysis, because many of our users, they stick just with basic data visualization, for example in Grafana. But in some cases, you need to go beyond this and use Python or MATLAB in order to make more advanced analysis of your data. And you might ask, why do that? And this is generally when you need to do more advanced modeling that is not easy to do via the existing tools we discussed. If you're just looking to get the average speed of a device over a specific time period, you can do that via Grafana or many other methods. But often you need to do things like, specific engineering algorithms or machine learning analysis or create digital twins. Maybe you need to model remaining useful life, as an example of an electric vehicle battery, which was the topic of another webinar we recently did with the MATLAB team. So there can be these cases where it's way beyond what you can do with Grafana dashboards, and it's way beyond what you can do with ad hoc analysis of the data. And in particular, some of these analyses can easily take hours or days to run the processing of the data, and you don't want to sit there and wait for that. It is also critical if you need to do data labeling, for example, for machine learning, where you are trying to, again, look at specific types of data patterns and then name these data patterns in a certain way. It could be a diagnostic event, or it could be a quick charge event, or it could be something else that you then feed to some prediction algorithm, for example. This type of stuff is again a good use case for more advanced data analysis. And as you could probably imagine, you can do this with the existing workflow as well. So you don't have to reinvent the wheel. If you have set up this pre-processing of your data, you now have a Parquet data lake. You also have Grafana, and both of these tools are extremely easy to work with through both Python and MATLAB, which are the most popular programming languages for our end users. And it's pretty easy to do this. You can see here for Python and MATLAB 2 script examples, and we have more in our CANedge intro on how you work with Parquet data with these tools here. But it's a few lines of code before you have loaded specific sets or specific data sets from your data lake, and then you can do whatever you want with this. So at the high level, it's very easy to get started, but there are some considerations you need to make if you work with this data at scale, because if you don't, then you'll get burned in terms of cloud costs and other aspects here. First of all, you need to envision what is going to be the end consumption of your data. You need to consider if your data analysis will imply that you risk going beyond the memory of whatever resources you have for computing this analysis. And you also need to consider that you deploy this in a way that will scale. Maybe you write a nice script for some quick testing, but that script might not be suited for scaling up to 2 terabytes of data, for example. If you look at the first part here, this is about ensuring that you upfront define what are the results that you're trying to get out of your analysis, and even go so far so as to create dummy results and figuring out how you wish to present these to the end consumers of your analysis. And you need to figure out what are the dimensions and the granularity of these results upfront. Like, do you need the results per device, per trip, per time period, overall per year, or whatever it might be? That is something you should figure out before you start processing the data. You should also figure out how you wish to store the results, and surprise, surprise, my recommendation is to store the data again in your S3 Parquet data lake and store it as Parquet files. Because if you do so, you can again visualize your data through Grafana dashboards or however you want to do it. You also need to consider that you may go out of memory when you process terabytes of data, for example. And you can do this in different ways. You can chunk up your data and do batch processing, where you essentially take small chunks of the data, process that, extract the result, put it into a list, and then move to the next chunk and do this in a loop, for example. And that's how many will probably start out. But there are also ways to abstract this complexity away. MATLAB has something called tall arrays, where you essentially say, okay, here is MATLAB, my 1 terabyte of data. I want to do these calculations on it. Please handle the complexity for me. And Python has a similar method through something called desk, which again allows you to just point to where all of your data is. And in this case, MATLAB and Python will handle this aspect that the data may be far beyond what you have in terms of memory, and it will chunk it up under the hood in a way that allows it to extract the results you want, but in much less code than if you had to do this the hard way, so to speak. And finally, when you deploy the analysis, you really need to consider how you deploy it. So AVS, as I mentioned in the start, is pretty cheap until it's not. So one example where it's not super cheap is if you pull the data out of AVS, you are paying egress fees, which cost you $90 per terabyte. Imagine you have a script that is running, 5 times per day, pulling all of the data from your data lake every time to get maybe the most recent update on some parameter. You are now pulling, huge amounts of data on a daily basis, and after a month, you spot that you consume quite a lot of money. So take care with this, but also consider that if you're pulling data down locally, you have latency. It takes time to pull this data, so it's not ideal to take all of your data out of the cloud, process it locally in order to get some result. In addition to this, even if you wanted to do this, your local PC may not scale that well. So we have some users that needed to do some data processing, and they extrapolated that it would take weeks to run it on a regular PC. And that makes sense because some of this is pretty high computation on pretty dense data. And that's where if you put it into the cloud instead, when you set this up, you can scale up the amount of CPU you allocate to this problem, and therefore you can do something in hours that might otherwise take weeks to do. So as illustrated over here as well, this means that when you deploy, figure out where you deploy as well. You don't want to do this workflow where you pull the raw data or the decoded Parquet data from these S3 buckets directly to your local PC and then process it. That's just going to be expensive and slow. What you could do is to take the data from your S3 output bucket and process it through Python in the cloud. That's essentially what this trip summary aggregation we mentioned before is doing, and also in a sense what the Lambda function is doing. Or you can use Athena as the interface, and you can do that through Python or whatever deployed in the cloud, or even through Python on your local PC, and just use Athena as the middleman for processing your data, because Athena will pull the gigabytes of data over here in the cloud, process it, and return the results for your analysis locally without actually pulling this data out of the cloud, and therefore you avoid the egress fees in the process. Finally, here at the end, I'll just mention some of the use case examples. To illustrate here, you don't have to set all of this up, and that's important for me to stress. We have tons of users that, for example, have many devices, deployed, but they only take care of the first part, the device management aspect. They make sure to optimize their file size and they collect data to S3, but they may only look at data on an intermittent basis, like if there is a reported issue, they need to be able to pull, the log file of interest, and they process it locally with one of the GUI tools on their PC. And that's perfectly fine. I'm not mad if you don't use all of the advanced workflows. This is more to say that there are many, many tools available, but you don't have to use all of them. Some of our users use some of these infrastructure tools, like for example, MGIL here, they deploy the basic pre-processing workflow and they deploy Grafana dashboards, which allows them to create KPI dashboards and do some basic predictive maintenance on their fleet. And they can do reporting and other stuff for their clients in a small truck fleet, as an example. The OEM Steel Wrist, they also add the trip summary aggregation. So as an example, they go and take the data, also visualize it in Grafana, but they also create this trip summary aggregation dashboard, which allows them to quickly monitor if there are any diagnostic events or any specific trips that look different from the rest in their Grafana dashboards. Then we also have cases where users set up predictive maintenance using event detection workflows like the ones we discussed. One example you can find in our case studies is this one where an OEM has around 250 plus AGVs, and they want to spot when these AGVs are going to burst into fire before it happens, essentially. And they do so by collecting data every 30 seconds, analyzing it for DTCs and high temperatures, and then they send essentially alerts to the relevant technicians in a response to this. And we also have many that do this in heavy-duty vehicle fleets as well. And just as another way that you can use these types of workflows, we have another case study, Actors, that essentially develop a small mobile app for operators of hay baling equipment, where they get, again, very frequent splits. Data is processed, put into a small database that is then fetched via the app, and that allows them to see, in near real time where the vehicle are, where the next essentially hay bales, I guess it's called, are that they need to collect. So many different use cases, but the essential fundamental workflow that enables all of this is pretty much the same. So this was what I wanted to cover in this webinar, and I hope it was useful. Again, as mentioned in the description of the YouTube video here and the live stream, you will be able to find a link to our article, and it does cover exactly the same topics that I have covered here. And if you want to set something up along these lines here, or you have questions, feel free to send us an email via our contact form, and I will make sure to answer and clarify any questions you may have. So what I will do now is just to spend a few minutes here to see if there were some questions in the chat, and I will try and cover those. And if you have additional questions, feel free to mention them in the chat now, and I will try to cover them as well. So we have one from Vishal here. How much data usually is generated and transmitted from mobile vehicles in mining per month? And this is a common question. We have in some of our other webinars some examples of this. If you have a normal J1939 single CAN bus network where you are recording everything, you might be looking at 700 frames per second. And if you use the default CANedge configuration file, this would be equivalent to maybe 50 megabytes per hour. And then you can start scaling it up, right? 10 hours of operation per day, that's half a gigabyte per day. And that means, 15 gigabytes per month in that case. If you actually compress the data, then you reduce it, then it's 7.5 gigabyte. And if you start adding filters and prescalers to optimize what you record, then in most cases we see it to be closer to half a gigabyte to 5 gigabytes, depending on what type of use case you have. So it's fully customizable. It all breaks down to how much data do you actually need to record. Let me see here. There is another question from Marcus whether the device can be configured remotely with over-the-air configuration. And yes, this can be done very easily. Essentially, the device will upload its own configuration file to the S3 bucket. And if you replace this configuration file with a new one, that will trigger the device to update itself the next time it synchronizes. And the simplest way to do this is by using this CAN Cloud tool that we provide, where you can log in and quickly get an overview of your devices, and where you can also directly configure each device and then submit the updated configuration, which will then trigger the update. And CAN Cloud will also tell you then when the device has synchronized with the new update that you sent. There is another question from Gilmero on whether we have publicly available CAN data that can be used, for example, for ML research. And yes, we have a number of data packs, as we call them. If you go to our website under our guides section, then you will find all of these. You can also simply sign up to our newsletter. Then you will receive in the first email a link to the different data packs we have. These include heavy-duty data packs, car data packs, but in particular it also includes this Kia EV6 dataset with more than 10,000 kilometers of data recorded from my car, which is free to use for this type of purpose. Then there is a question on the decoding process and whether there are any workflows using MQTT or other protocols on the market. And you can say MQTT is a great protocol for streaming small chunks of data to, for example, a server. The CANedge records huge amounts of data potentially in some use cases where you might be generating, let's say, 5 megabytes of data per minute in some of the more extreme deployments. And MQTT does not really, or is not well suited for that, which is why we instead use HTTP, HTTPS, and upload via the S3 interface to these S3 buckets. So we do not have, you can say, the MQTT equivalent necessarily, because it's not a good fit for this here. Then there is a question on the MF4 file format and whether it is resulting from a specific protocol. And no, that is not the case. It is rather an industry standardized file format for storing CAN bus data as well as other automotive data like Ethernet and FlexRay. It is defined by the ASAM organization, and there are different tools that natively support this, like ASAM MDF is an open source GUI tool we recommend, but also tools from Vector, for example, support the MF4 file format natively. Then there is a question on whether we in the analysis process use AVS Databricks or another service, or whether we only use, Lambda functions. And we don't use Databricks or something like that because for the use cases that we have experienced so far, we find that the Lambda function provides the simplest and lowest cost, as well as, I think, the most transparent way of processing the data, which enables both ourselves and our end users to troubleshoot the decoding quite easily. For example, you get an alert if one of the Lambda invocation fails, and it's quite easy to then go in and review the output data to see, maybe there was an error in your DBC file or something else that caused this. Then there is a question, is there a cloud-optimized MF4 format to distribute access before converted into Parquet format that is already naturally cloud-optimized? And if I understand this question correctly, it might be whether the MF4 file format itself could be used as a data lake. And we have examples of this. One case study is with Vitesco, now part of Schaeffler, where they actually do the processes we have discussed here, but they essentially DBC decode their data into MF4 files, now just containing DBC decoded data, and that's another way of storing this for different use cases. The MF4 file format also supports a more cloud data lake type structure, but it is not something that we work with because we found it to be far less interoperable and far less supported by popular tools compared to the Parquet data lake alternative. Then there is a question on whether you need in heavy mining equipment to have multiple CANedge units to be deployed in order to collect data. And this is a good question. A single CANedge allows you to record 2 separate CAN bus networks. And for many use cases, this is sufficient. But we also have many OEMs that work in mining, and they often have mining equipment with 3, 4, 5, 6, 7, 8 CAN buses that are parallel and where they may want to record all of them. A year ago and before, this was done by these users essentially deploying 2 or 3 CANedge units separately in the vehicle. But this has a number of downsides. For example, it's expensive and the data is not perfectly time synchronized. And as per the workflows discussed here, you would get multiple log files that you would have to manage. Not ideal. Today, and as of last year, we have a small add-on device called the CANmod router, which you can connect to the second port of the CANedge, and that allows you to take 4 isolated CAN bus networks and transport them using a transport protocol into a single CAN bus. The implication is that a single CANedge can now record 1 CAN channel through the first CAN1 and 4 CAN channels through CAN2. And all of the workflows we have discussed today will natively allow you to essentially restore the original CAN buses, effectively making it as if the CANedge had 5 CAN bus channels in total. And you can go beyond and daisy chain multiple CANmod routers. So we have some of our OEM users today that are essentially recording 9 CAN buses with a single CANedge by using 2 CANmod routers as part of this. So this is useful if you have more than 2 CAN buses to record. Then there is a question, how much time does it take from the time it collects the data to visualize the data? Could we achieve real-time monitoring? And the fastest you can get there is that you can set up a split time of 10 seconds. This means that every time 10 seconds have passed, a new log file is ready on the SD card and will be uploaded. Let's say that takes 2 seconds. On the server, this will trigger the Lambda function, which will process it and make it available in the data lake. Maybe that takes 1 or 2 seconds more. So typically you should count on maybe 15 seconds or 20 seconds delay for a process like this in order to see the data, for example, in dashboards, or to trigger some event or alert that you might have. And today the device is not designed as a real-time monitoring piece of equipment. It is a data logger, and that's what it's designed for. So you can get near real-time data logging in this way and visualization, but it is not the core use case for the CANedge. Then there is a question as since Modbus is also very popular in the automotive, could the CANedge handle such a protocol by using a third-party device? And I don't have a specific suggestion, but it's a good example that we will most likely continue to look into creating more of these CANmod devices, like our sensor to CAN modules, and a bit like how the CANmod router lets you take 4 CAN buses and output 1 CAN bus. We could see potential for a device that would take 1 or 2 or 3 or 4 mod buses and output that data as 1 CAN bus, and the same for FlexRay and other things. Maybe there are tools on the market today that do this, but I don't have specific suggestions. but if there are, you could use them with the CANedge as long as they output CAN bus data. Then I think there's another question on how much the delay is in AVS or local S3 in the system. What is the maximum loss in real time? And I think this is answered previously about how fast can you get from data being uploaded to data being available. Then there is a question on whether you can sort of change so that you maybe record data once a minute, but some event happens and you send more data. For example, you send log files at a higher frequency, or you send more data based on some trigger condition. And as explained previously, the maximum frequency you can get are these 10 seconds here. So you cannot change that. But in response to an event, as we also explained in the full article on this topic, you could, instead of sending just a notification, you could also trigger an over-the-air update of the device, so that if event XYZ happens, you will actually make an update to the device to, for example, for a period, change the configuration to log more data than you might normally do in order to get more diagnostic information in troubleshooting this event. So that is possible, but it is more of an advanced workflow. Then there's another question on the MF4 file format and the DBC file format. And I should mention, if you go to our website under guides, we actually have a detailed introduction article on the MF4 format as well as the DBC file format. And the other webinar on CAN bus data logging also covers this in more detail. So I recommend to check that out. There is a question what physical interfaces the CANedge support based on different OEMs such as Komatsu, CAT, Sandvik and others, or Caterpillar, Sandvik and others. And I guess this question is whether the CANedge will allow you to record data from these vehicles. And the short answer is yes. The CANedge does not care about which vehicle it is. It just records the raw CAN bus traffic regardless of whether it is one brand or the other. But what can be tricky is how you find the relevant CAN bus in these mining vehicles. That's step one. And even if you access the right CAN bus, then you will need to decode it. Here, a standard DBC like the J1939 DBC may allow you to decode a lot of the data, but not necessarily all of it. But again, we explained that in the other webinar in detail. Then let me just check. There is another question about MF4 versus MDF, and these are the same file formats. MDF is sometimes the reference for the MDF file format in general. MF4 is also used. It is essentially the file extension, so the files would be named .mf4. So they are used a bit interchangeably in different cases. There is a question about how we integrated the CANedge in a car, and we essentially provide adapter cables for pretty much all of the common use cases, including a DB9 to OBD2 adapter. And then it is just a matter of transmitting requests into the car. So we have guides for how you would request OBD2 data from, for example, gasoline and diesel cars, and also how you can request data like UDS requests for electric vehicles. And we provide some case study examples for some of the most popular vehicles like Tesla and Kia, Hyundai, Volkswagen vehicles and others on our case study section on the website. So those are also available. Then there is a question about, let me just see here. There is a question about whether a machine, I guess like a vehicle, would provide historical data via the CAN bus or if it's only current data. And generally, a machine where you record data from will normally only provide current data, as is also explained below, except that sometimes there may be some level of data stored through historical trouble codes or similar that you can extract on a request basis. Then there is again a question about real-time streaming for transportation, and I think we have discussed this, that the CANedge is essentially a data logger, but can provide near real-time data. Then there is a question if we will share this video, and you can actually just use the existing link for the live stream. That will be where the video will be based afterwards, so you can find it on YouTube. Then there is a question about if you use a CL2000 or one of our data loggers and you supply power from, for example, a motorcycle battery, will that device continue to consume power even when the device or when, I guess, the ignition is off. And this depends on the vehicle. Some cars, for example, will keep powering the device when the device is connected, even if you've turned off the ignition. In other cases, the car's ignition will be linked to the power supply via, for example, the OBD2 connector, and the same goes for other vehicles. It's a bit case by case. If you have a device that is connected, then it's typically not an issue because the consumption of our devices is 1 watt, so it's quite low. But if you are requesting data, for example, OBD2 requests into a car while the car is turned off, that is a problem because it will drain the battery much faster. And that's why the CANedge allows you to use these triggers I mentioned to start and stop transmission of data. So for example, you can say if the GPS-based speed is below 0.1, do not send any requests into the CAN bus. And that way you can avoid battery drainage. And then there are some questions like if you have an issue with a specific vehicle, how do you solve this? And here I would recommend to contact us. It will depend vehicle by vehicle what you can extract in terms of, for example, OBD2 requests. But there are also ways to make a more structured manner of checking what is actually supported by the vehicle rather than just trying out the different CAN IDs or different parameter IDs. And in our CANedge intro under the record section, we explain this in our OBD2 section. So I recommend checking it out, but otherwise send us an email. And then there is a question as to whether we would release a version of the CANedge with both Wi-Fi and LTE. And we sometimes get this question here, and most likely we will not. We try to design the devices to be extremely compact, and if we were to have both connectivity methods in the same device, it will both increase cost and the form factor quite significantly. And our opinion is a bit that if you have a use case where you are collecting data from, let's say, a vehicle on the road, if there is reasonable connectivity, you would normally see all of this data being offloaded via LTE, even if that device had access to Wi-Fi connectivity when it returns to the garage. But there could be a use case in the case where you are having very intermittent LTE connectivity, and you would then want to offload the data periodically when it returns to the Wi-Fi. But for such a use case, I would probably recommend using a CANedge 2 and then simply only uploading the data through the Wi-Fi network where that is available. Or you can go a bit of a mix and use a CANedge 2, deploy it with a cellular hotspot as the router in the vehicle. That will allow it to offload data while on the road. And then as a secondary Wi-Fi network in the list, or as a primary Wi-Fi network, you can then have your garage Wi-Fi so that when that is available, it uses that instead of the USB cellular router. Then there is a question regarding Grafana roadmaps that I think are probably best to ask on their GitHub or send us a contact email. And then there is a question about what model I recommend to get data for machine learning process in trucks Euro 6. And it doesn't really matter so much what the vehicle is. For me, it is more a question about the questions or the parts we discussed before, whether you should go for a CANedge 2 with Wi-Fi or a CANedge 3 with LTE, which depends a bit about the circumstances for your use case. But you can always send me an email and we could go through this in more detail. Then there is a question here at the end, if I can give a bit more detail on fleet updates and how customers would be able to do this for multiple devices. And we skipped over this a bit. You can do it through, for example, CAN Cloud and do it device by device, but it is a bit cumbersome. If you have many devices you need to update over the air, you can go to our GitHub page and find a tool called CANedge Manager. And this is a command line tool where you can scale up the over-the-air update to multiple devices. And you can also use it to write your own Python scripts and logic for how to update your fleet. And I think in particular this tool is useful if you are also encrypting your passwords, because that makes it much easier to handle that as part of the update. So check that out and send us an email if you have issues using it.